Let's look at something that by now you know, the convolution product. The convolution product, it is when we take two functions to produce another function. So define f of t and g of t as given functions, right? Then the Fourier transform of f of t convolution g of t is equals to an integral from negative infinite to positive infinite of f of tau g of t minus tau d tau. This thing here, this thing here, what you see here, it is your third function, right? So what we are going to learn really is that if you find the convolution product, of f of t, g of t, you actually find the Fourier transform of each function. So that is the proof for today. So we know that the Fourier transform of f of t is f of j omega times the Fourier transform of g of t, it is g of j omega, and both are sinc of j of a omega. So both of them will result to a omega. Now, what is the proof of this? So the proof will be show that the Fourier transform of f of t convolution product g of t, it is equals to the Fourier transform of f of t times the Fourier transform of g of t, which is equals to f of j omega times j omega. So we need to show this. Now, and the way that we are going to show this, we are going to use a theorem that we learned previously. It's called the Fourier integral theorem. I'm too far. The Fourier integral theorem. It is this theorem here, this theorem. So keep this theorem in mind, by the way. So the way you're going to prove this, you're going to say an integral from negative infinite to positive infinite of an integral from negative infinite to positive infinite of f of tau g of t minus tau e to the power negative j omega t dt. Now in this case, you can see that we have a problem that we want to integrate. Can I remove this part? We have a problem that d tau e minus j omega t dt, we have to integrate this in a function in terms of tau, but we have a function there, and this e will only satisfy the dt. So how can we work this through? We are just going to make it very simple by saying let v to be t minus tau, and t will just be v plus tau. In this case, dv is equals to dt, right? If we do that, I'm going to have an integral from negative infinity to positive infinity of an integral from negative infinity to positive infinity of f of tau g of v, like that. dv d tau e to the power negative j in bracket. So what is your value of t? Your value of t, it is v plus tau dv now, right? You can actually see that you can separate the e, right, from negative infinite to positive infinite, integral of f of tau gv d tau e to the power negative j omega v times e to the power negative j omega tau dv, and then we can do the integral thing. So since we have done two integrals, we can do the product. So we are going to say an integral from negative infinity to positive infinity of f of tau e to the power negative j omega tau d tau times an integral from negative infinity to positive infinity of g of v e to the power negative j omega v dv. Now what is this? This is a formula. You need to recall that the Fourier transform of h of t is equal to an integral from negative infinity to infinity of h of t e negative j omega t dt will just equals to h of j omega, like that. So this part here, that part, it is f of j omega, f of j omega times this part here, it is g of j omega. So this is the proof of the convolution product. There is not a lot here, but we are going to use the convolution product when we do the inverse of the Fourier transform. See you on the next one. This one is quite short, but see you next one. This is the convolution product.